Welcome back to the KE Learning DIY Organizational Design course. We're still in Chapter 2, where we're breaking down the framework with which we're going to perform our DIY organizational design process. We covered the organizational design components of process and people in Chapter 2.1, and we're now going to cover the rest of the components in building our DIY organizational design framework. Let's get going. The remaining components we're going to deal with now are data and systems, which are interlinked in some parts of their functions and operations, and somewhat strategically and operationally dependent on each other in other parts. We start with data, where the subcomponent breakdown includes data collection and storage, which involves gathering information from various sources, organizing it in a structured manner, and then securely keeping it in a designated location, ready for analysis and future use. Data ecosystem optimization involves improving the efficiency and effectiveness of a data ecosystem in order to ensure that data flows seamlessly, is accessible, secure, and actionable, enabling maximum value extraction from data assets. Lastly, data management and usage optimization deals with efficient collection, storage, organization, maintenance, as well as the utilization of data. The result of this is effective decision-making, where effective strategic business landscape navigation, efficient operations, as well as impactful innovation that derives high business value, are the order of the day within the given business or organization. These subcomponents distill into a process, the first step of which is the collection of the necessary information that would allow for a good view of the current data context within the given business or organization, which would then allow for a deeper understanding. This understanding should provide insights into the key issues that need to be dealt with in order to arrive at a future data ecosystem that would place the business or organization in a better and stronger, data-driven position. Once the picture of the potential future state of the data ecosystem is formed, it can then be optimized to suit key internal and external contextual factors of the organization, including opportunities, strengths, and limitations, both within the organization as well as externally in the business landscape within which the given organization operates. We then need to figure out how to move from the current state to a future state in a manner that not only does not materially disrupt the current operations of the business, but also does not cause so much disruption to the data ecosystem itself, such that the situation gets worse than it currently is. A solution that is tactful and measured from a disruption and risk management perspective has to be designed to ensure this process is carried out in a logical and methodical manner in order to ensure as little disruption and risk as possible. Planning the implementation of this migration is the next step of the process, where key internal organizational factors such as available budget and resources have to be taken into account to lay out implementation roadmapping and associated timelines in order to fully move the ecosystem to the future state. Distilling this process further reveals that the key information that needs to be collected includes a list of systems in the current landscape, each of the system's functions, that is, the function that they actually perform, along with the data they need to perform this function. This includes the data the system needs as input, the data the system generates in the performance of the function, as well as the data that is extracted from the given system, or that the system spits out, as input to either a process or another system, in order for that process or system to functionally operate. The type of data, state of data, and the storage layout of the data across all the various systems in the current way of doing things are also a key piece of information to collect as input to this process. The secured data storage layout and design is the first component of the data ecosystem we choose to start with. As they say, data is currency and the lifeblood of any business in this digitally advanced business era, and therefore needs to be secured and stored well in order to be able to derive value from it. It needs to be clean, it needs to be accurate, it needs to be unduplicated, and it needs to have a proper storage layout, otherwise, as they say, garbage in, garbage out. The layout of data storage is a key part of any organizational or business data landscape, so let's unpack it a bit more. So in many instances, the systems in the business or organizational system landscape are the main source of data within the organization, be it user-generated data inputted into these systems, the data the system generates itself, the data that the system transforms from user-inputted data, as well as the data that the system transforms from data it generated itself. These are systems that are in the organization's system landscape to perform a range of functions, from administrative operations systems, such as accounting and bookkeeping systems, core customer operations systems, such as customer management or customer relationship management systems, payment and core business money flow systems, as well as core product or services dispensing systems such as an order management system. Other system types include business support systems, such as systems that are effectively a set of applications that help the business manage its operations, incorporating a range of functions described above into one large system, from order management and billing to customer relationship management. For purposes of effective tracing and extraction of data in the design or operation of a data ecosystem, it is worthwhile to separate all these applications or subsystems that form part of this large system and denote them as standalone data sources. Other sources can include data collected from core operations or business model-related systems, such as IoT systems, or solution ecosystems that generate and store IoT device data, for example, basically any system that generates and stores data within the organization. Other examples include customer-related data, such as existing customer demographic or payment method data, to operations-related data, such as number of tickets sold on a given day, at a given location, if the business is a cinema or an arcade, or number of ice cream cones of a certain flavor dispensed across machines, across outlets, across locations, if the business is an ice cream parlor. Now, once this data is extracted from the various systems, cleaned, stored, and secured, there are two ways that its storage layout can be structured for maximum benefit of the organization from an overall business value management perspective. We can either design the storage layout by function, where we identify and extract key data related to each specific function, and store it in a specific data storage pod that will contain all the necessary information needed for data-related activities, such as insights generation, process automation, reporting, and so forth, for that particular function. So each function within the organization, be it customer operations and management, human capital management, or finance, as long as it's a function that exists within that organization, it will have its own data storage pod, where every piece of data related to that function is stored and updated as needed. Using this data storage layout approach means that within a particular function's data pod, there will be smaller data pods that relate to each of that function's subfunctions. So essentially, the data pod for the entire function will be built by collecting data needed to perform operations, decision-making, or reporting for each subfunction, stored within a subdata pod created specifically for each subfunction within the main function's data pod. The main functions pod will also have its own overall function-specific data storage location, especially for data related to the function's overall insights and reporting. These data subpods within the main functions pod can be distilled to a level that makes sense in terms of the size of the pod, as well as the intended usage of the data to be stored within the given subpod. For example, first level is the overall function data pod itself, within which the distilled subfunction pods are stored, within which subfunction distillation pods are stored, and further distilled if required.